um, to the stream, to the people. Conor Tompkins.
All right, thanks, Colin. Thanks for Code and Supply for hosting. And I think this is also a joint PyData event as well, so thanks to them. All right, my name's Conor Tompkins. I'm a data scientist. I work at Shaw Industries that's based in Georgia. They manufacture and sell flooring, a lot of soft surface like broadloom, carpet tile, also resilient tile and plank, things like that. I work in supply chain. I do a lot of demand planning, customer demand, and that involves time series forecasting. I'm only speaking on behalf of myself, not my employer. These are, just some tips and tricks I've picked up along the way, but solely, it's my own stuff. All right, so what is time series forecasting? It's the practice of making predictions about some quantitative value in the future. And even beyond that, it's about understanding the distribution of the forecast in the future. It's not just the average of the forecast, it's what's the distribution of the forecast, what's the prediction interval. Typically, we're interested in predictive accuracy, so how close our forecast is to the actual observed events. We're not interested in inference, understanding causality, things like that. This is more closer to the machine learning style of accuracy is our metric. So what is a time series? It's data collected about some quantitative variable over time, and it's collected regularly, right? Every year, every quarter, every month, every week, day, half hour, etc. Every is the key there. It has to be regularly collected. There are ways to do non-regular time series, but that's a lot more complicated, and I'm ignoring that for now. So some examples, customer demand for a company's product, like how much carpet are people going to buy next month, next year. Electricity usage, stock price, network latency. I've seen examples of people in server farms using time series analysis to detect outliers, to see if some maintenance needs to happen on a given piece of hardware. Pothole reports is the example that we're going to use today. So this is data submitted by users of the 311 system in Pittsburgh. So if you see a pothole, you can report it. That gets logged in the system, and that has some interesting trends and seasonalities that we can explore as a good example here. So this is just an example time series. This is peak daily demand for electricity in Victoria, Australia, which is where Melbourne is. So it's Australia, so their winter is in June and their summer is in January. But you can see that it's driven largely by heating and cooling, as you might imagine. So people put the heat on in June and put the AC on in January. It's pretty seasonal. There's some weekly effects here, like weekday versus weekend, but there's also some monthly effects, right? This is from 2012 to 2015 again. And it also changes variance a couple times, but that's also seasonal. So this is a more complex example, but this is sort of the stuff that you might deal with in forecasting. So what can be forecasted? Not everything can be, and sometimes that's most of the game is understanding when you just can't do it, and you need to try a different approach. But typically, you understand the data generating process. So for that previous example, it's residential and residential and commercial demand, driven by mostly temperature, so heating and cooling. I think they strip out heavy industry in that data set, so it's not for like smelting and things like that, like really high intensity stuff, which would introduce some more spikes and make things more complicated. Is there historical data, right? If there's no data, then you can't make a forecast. You're making a loose assumption that the future is going to be similar to the past. Again, it's not exactly the same as the past, otherwise you wouldn't need to forecast, right? But there's some loose similarity there. And no environment is stable, no system is stable, right? Things are always changing and have always been changing and will continue to change in the future. But if you can assume that things will continue to change as they have changed in the past, then we can start working with that. And then, is there going to be a feedback loop? Is the forecast going to impact the quantity that you're trying to forecast? Is the forecast going to change the behavior of the users of the forecast? If that's the case, then that's really complicated and you might need to try something else. One example there is, how much will it rain tomorrow versus how much will it rain on you tomorrow? I can predict how much it's going to rain tomorrow based on weather history, right? If I tell you it's going to rain 6 inches on you tomorrow, you're going to stay inside. And it's not going to rain on you at all, right? So that's the efficient market hypothesis, is that information is already baked into the user behavior. So forecasting there is not going to help you. So why forecast at all? It's about making better decisions, right? If we know more about the future, we can make better decisions today to plan for that. In most business, industry use cases, it's about resource allocation or acquisition. If you need to buy stock to sell to a customer, you can forecast customer demand and then use that for your stock plan, right? Things like that. There's also the forecast horizon is important. So there's short, medium, and long term. There's what's the demand for power going to be in the next hour? What's the demand for flowers going to be in 5 months? What is the demand for a company's product going to be in 4 years? And accounting for changes in population over geography, right? If people are moving, do you need to open a new store in the southeast or something? So how are we going to forecast? So a typical regression model, you would model the pothole reports as a function of some set of explanatory variables, right? So you could use the year, the month, and that would give you some sort of trend in seasonality. You could use weather variables like rain and temperature difference, things like that, to get the freeze-thaw effect. Maybe if the public works is going to increase or decrease their budget, that would change how well they're able to get on top of road repair and prevent potholes. So that might be a variable of interest. The time series approach is more, it more focuses on the actual target variable and less on exogenous or outside variables. So it's using the previous observations of the variable to predict the future of that variable. So here we're going to use the next observation of pothole reports, which is 2+1. We're going to model that as a function of the current pothole reports and the previous observation and the previous observation, et cetera, et cetera, et cetera, plus some error terms and things like that, because no model is perfect. This is not an exact model, just a framework. So this is autoregression. It's regressing the variable against itself, basically, some transformation of itself in lagged terms. So why use time series models at all, right? Because most of the time, if you're interested in time series things, there's some degree of autocorrelation involved. So observations that are closer together in time are going to be more correlated, and observations that are more distant in time are going to be less correlated, or maybe negatively correlated, right? So if you do a traditional regression model on that, you might get some correlated errors, which will cause problems in your predictions. The time series models tend to do a better job accounting for that autocorrelation. So this is the process we're going to use. Pretty standard if you've ever done machine learning work. We're going to do some exploratory data analysis. We're going to compare some models, do some model selection, and then make a forecast and evaluate the accuracy of that forecast. All right, I can stop yelling now. So we're going to get into some R code now. I know some people here have experience in R or in Python pandas. This should look familiar. If you have questions about the code, I prefer to hold off on that, and I can get really into the code after the main talk. So the data structure of a time series in R, and I'm using the Fable package. There's Fable, there's Fable tools, there's Feasts, and there's Sybil. It's like a family of R packages that all work together to make this whole process pretty streamlined. So this is a time series table. It's got a key, which is the request is the type of request, which is the potholes. That tells us how to group the data. We have our create date, which is the date that the report was created on. And I'm transforming that into a year month string, and that tells us the order and sequence of our data. And then the measured variable is report count. So that's the basic structure that we're going to use from here on out. So here we have 106 observations, which means 106 months of data from that 311 service. So, and it on the top right there it says 1M. That's the frequency of the data, right? So it occurs every month. If it was quarterly, it'd say 1Q, or if it's yearly, it'd say something else, right? It has that metadata about the frequency embedded in the structure of the data. So this is just some basic exploratory analysis, make some basic graphs. This is just the count of reports over time by month. Definitely has some seasonality in there, right? Spring is the big time. Really tapers off after that. But there's also some interesting trends. You might say that there's two distinct trends and maybe a knot in the trend in 2018. So there's some sort of curvature there. So any model that we choose will need to be able to handle that trend and seasonality appropriately. Any questions so far? All right, this is just another exploratory graph. Each line here is a year. The colors probably aren't great on the screen, but each line is a year, and then the months are on the x-axis there. So this shows that seasonality in spring. It picks up in February through May, and then really tails off. But there's significant variation by year. This is a sub-series chart. So it shows the months across years. So each panel here shows a month, and the years on the x-axis. So again, February through May is the peak period. The blue line shows the average of the month, but again, there's some interesting variation across years. And again, this is pretty straightforward code. I just have my data frame. I feed it into the GG subseries function, and then do some additional. I add that one extra line to facet it out by month and create those panels. So pretty straightforward. Just 2 lines there. You can also do a time series decomposition. So this will split the time series into a trend, a seasonality, and then the remainder, right? And the trend is the trend of the data accounting for seasonality. The seasonality is the seasonality of the data accounting for the trend, and the remainder is everything else. So the trend, you can see it increased through 2019, then dropped off steeply, and then picked up a little bit again in 2022. The seasonality has actually shifted over time. There was a plateau, like a two-stage plateau there for the first 3 or 4 years, and then it transitioned into a single peak month. That's actually a more complex time series behavior, I would say. This is pretty small data, so we're not going to be able to really address that. But over a longer time series, you can see that the seasonality can shift over time. So more complex models will be able to handle that better. And then the remainder there is everything else, right? So we have that set of outliers in winter of 2017 and 18. I remember that it was pretty wet and nasty. So just anecdotally speaking, like that makes sense. You can also do some outlier analysis here. So this uses the interquartile range of that decomposition and identifies those outliers. So each red dot is an outlier. So this is an outlier accounting for the trend in seasonality, right? If you just took the average or just took a trend or just looked at the seasonality, you would miss the combination of those things. So this outlier analysis will account for all those things. There's more complex approaches. This is pretty basic, but I think it does a pretty good job. All right, so we're going to get into the modeling here. So this is pretty classic machine learning stuff. We're going to split our data into a train test split. You always want to evaluate a model based on data that it hasn't seen before. Otherwise, you're going to really overestimate the quality of your model. So here I'm taking the last 20% of the data in sequence and using that as the test set and setting aside everything else as the train set. So first 80% train, last 20% test. So these are some of the models that are available in the Fable R package. There's not all of them, just the ones I tend to use first on any project. And I'm going in order of simplest to most complex. So a naive model is simply taking the last value, the last observed value, and playing that forward across the forecast horizon. So if you want to know what November is going to be, use October. And if you're forecasting at 12 months, you're going to use October 12 times, right? That's most likely going to be wrong, but these are all more benchmark models. And if your more complex model can't do better than these, then you should rethink your approach. So seasonal naive is just playing the last seasonal value forward. So if you want to know what November is going to be, you use last November. And same for December. It's a 12-month lag. And this is for monthly data, right? If it was quarterly, you do a 4-quarter lag. You can take the mean of the entire series and play that forward. You can do a rolling average by using the window function in the mean model. Again, these are benchmarks, but you might be surprised how often they're pretty effective. So now we're getting into the more complex models that can fit more interesting patterns in the data. So first one is the time series linear model. So we're going to fit a model along the trend of the data. It could be increasing or decreasing or flat, right? And then you can also use the seasonal function to add dummy variables for seasonal effects. So if it's quarterly, you have 3 dummy variables. If it's monthly, you have 11, because you always want to leave one out. Otherwise, your model is going to be rank deficient. Exponential smoothing is basically like a weighted average that weights the observations based on the recency. So the more recent observations are going to be weighted more heavier, and observations further in the past are going to be down-weighted. ARIMA is the autoregressive integrated moving average. This is one of the more complex models. I'm not going to get into the theory of it because it's pretty complex, but it can handle really interesting patterns. You know, if there's a curve, if the, like in our previous graph, if the trend has changed over time, it was going down, then it goes up. ARIMA can figure that out, whereas a linear model can't. It can also handle seasonal effects. It can handle longer time series. It does a pretty good job. The Fable package will automatically find the best model parameters. You can do that. You can, if you're interested in testing it out manually, you can always set those yourself. I tend to just let it go and find the best ones for me. And there's more models in Fable, and you can always make your own extensions, add your own models. Sorry about that. One note is that the time series model and the ARIMA model can both use exogenous variables to bring in information from outside the time series. So in the pothole example, you could model the time series with the trend and seasonality, but also bring in the amount of rain that fell and the min and max temperature, stuff like that. And that'll add, you know, it might add a little bit more accuracy. You know, it depends on the data, right? There's no free lunch, there's no best model that applies to everything, right? It all depends on the data. So here we're going to fit the models on the training data. So I'm taking my data underscore train table and piping that into the model function, and then I'm defining each model. So each model is a row. You'll notice that I'm transforming the target variable, which is report count. So I'm adding one and then taking the log of that, and that will guarantee that the forecasts are always going to be positive, because you can't have negative counts of potholes, right? That's something that's harder to do in other forecasting packages. Here it's handled automatically. You just wrap the target variable in some function as long as it can be reversed. And then when you forecast, it'll automatically be back transformed into the native units. So here's a model table. So we only have one request type, so we have one row, and then the other 8 columns represent the models. So the model is stored in that column. So these are just the models that we fit in the previous slide. It tells us a little bit about the model. So with that ARIMA model, we can tell that it's set a seasonal ARIMA because it has 2 PDQ terms, or a pair of terms there. You can also inspect a model to dig a little deeper. So this is the linear model of the seasonal effects. If you've ever looked at the output of a linear model, this should be familiar. We have our residuals, we have our coefficients. We have intercept, trend, and then 11 dummies for the months. In January is the reference one that's left out. And then we have, you know, things like R squared and stuff at the bottom. That's all pretty standard output in Python or R. This didn't turn out quite on the projector, but the black line is the actual. So this is the training data. The black line is the actual we saw earlier. The orange line is the within sample forecast from the exponential smoothing model, right? So you know it does a decent job. It gets the shape right. Does really well in the summer when there's a very low number of reports. But typically it's low or misses the shape on the peak months. But you know it does a decent job. All right, so now we're gonna forecast against the test data. So I'm gonna use the forecast function from Fable. I include the model table in my test data, and that will make a forecast for each model against that test data. So here we have 168 rows because we have 12 months for each model. or yeah, 12 points for each model. So we have our request type, which was the key. We have our model now, the model name. We have the create date, which is our index. And then we also have the report count, which is reported as the full distribution of the forecast. So it's not the average or the median or some percentile, it's the entire distribution. And then we can extract any percentile from that we choose. They also provide the average of that distribution. That's the point forecast. But this is why the Fable package and that family of packages is really helpful, because it makes it really easy to do probabilistic forecasting, which is really important in business, because if you just look at the average output and you don't understand the tails or the shape of the distribution, you're going to miss some stuff. Accuracy. So I skipped a fair amount of the available metrics. These are the two I go to typically. So root mean squared error, just on average how far off of the observed value is the prediction. That's for the point forecast, right? That's the comparing the average to the actual. And then we have our continuous ranked probability score, which measures how well the distribution fits the actual observed value. So it's going to penalize models where the observed value is outside of the forecasted distribution. And it's going to prefer models that give really tight distributions with really narrow prediction intervals, because it wants models that are more confident, right? If the intervals are more narrow, that means the model is more confident. But there's many more available in the Fable Tools package. These are just the two I go to. And then I transformed the CRPS metric with the scale function, which compares that CRPS for that model to a benchmark model. So yeah, it's nice that it does this, but but is it doing any better than some benchmark model? It's very simple. So then we're going to evaluate the accuracy of our forecast based on the full time series. So we're going to get our test accuracy here. So we have our forecast. We're going to pipe that into the accuracy function, compare it to the full time series, give it a list of accuracy measures, and then create that skill CRPS metric that I misspelled in the code. And then I clean up some column names and sort by the scale CRPS. So this is the list of accuracy metrics by model, sorted by the one with the best scale CRPS. So the seasonal linear model is best, and it also has the second lowest root mean squared error. So it does well on the distribution and the point forecast. So I'm going to go with that one. In this example, it's pretty clear, I think, but in other cases, you might need to make a different decision based on some business logic or something. And of course, the naive models do worst, right? Because they're very basic, nothing complex. But it's affirming that the time series has an interesting trend. It definitely has seasonality, so it's more complex. So you need a model with more degrees of freedom that can handle some more variance, right? There's the bias variance trade-off, more or less. So we're going to plot the top three models. We're going to plot those forecasts. So comparing those forecasts against the actuals. So our black line is the observed values, and then the dark line that's colored is the point forecast, and then the bands are the 80th and 95th percentile intervals for the prediction interval. So we'll start at the bottom. The linear model is basically flat, a little downslope, not much. The point forecast is always going to be a little higher, a little low, because it's a straight line. But the prediction intervals give pretty good coverage, which is why it ended up higher on that scale CRPS score. The ARIMA model is actually pretty high early on, but then it evens out, and the prediction intervals are very narrow. So that means that the model is very confident about the area that the observed value could fall in. And then the seasonal linear model that does best, again, a little high early, and then a little high in the next spring, but not that far off, and the prediction intervals give really good coverage. Any questions on anything so far?
Would it use a cyclical trend that isn't seasonal, like maybe something on like a 5-month interval? Can these models like account for finding something like that?
If it's, well, that would, in the strict time series definition, that would still be seasonal. If it repeats at a regular frequency, then it's seasonal.
It doesn't have to even divide into like a year.
No. As long as it could be every 5 months, every 7 months, whatever. You might need to use a more complex model, but it would be able to figure that out because of that autocorrelation effect. Now, if it's something like a business cycle, where the economy goes up until it doesn't, sort of thing, that's not seasonal. It's not doesn't happen regularly. That's much harder to control for. But if it happens at some frequency, then you can model that. But that's a good question. So we're going to refit our best model on the entire time series. The same model that we fit before, just on the full data set. And then we're going to forecast that out 12 months and make a plot. The forecast function takes a horizon argument if you're making a true forecast, and it automatically builds out a new data frame that it will fill the predictions in for you. And then I'm only going to show the forecast and then the data from 2021 after. And that's what our forecast looks like, right? The dark blue line is the point forecast, the average of the distribution, and then we have our 80th and 95th percentile of the prediction intervals. So the point forecast shows that it sees a continuing downward slope. It's slight, but it's still downward. The intervals are tighter in in late summer, and then they get wide in the spring, but that makes sense because that's where the most variance was in the time series. If you think back to those exploratory graphs that we made earlier. All right, so this is the book that I use to learn a lot of this stuff. It's a great resource. It's entirely free online. Forecasting Principles and Practice in this 3rd edition. Entirely free. All the code is available. Has a lot of great example data sets you can use. It's a great resource. Even if you're not interested in the code itself, it has a lot of good theory in there. All right, that's the main part of the talk. So yeah, we can take any questions now. Yeah.
Is there a point where you removed all the January records, or did I misunderstand that when you were like doing the +1 thing at one point in the code?
Oh, yeah. So I'll just go back. So the +1 thing was the transforming the target variable. So it just adds 1 to the count of reports. So if it's 0, then it's 1, and then it takes the log of that. So that'll coerce it to be positive, right? Then the January thing you were talking about, well, might have been about this, with these dummy variables, right? So January is not there. There's 2, 3, 4, 5, all through 12. But if you fit a model with every possible type of, or every observation of a categorical variable, it's going to be rank deficient, and depending on your software platform, it might explode, or just say I can't do that.
It's a regression, like, thing.
Yeah.
A regression problem.
Yeah.
But with that same question, like, if you, January seems like, I guess that becomes like a weird baseline. You just need to interpret it kind of without seeing it.
Yeah,
Wouldn't you maybe want to drop like a less important month, right?
it doesn't change the reference category, the reference month won't change the actual prediction. It'll only change the coefficients.
Okay.
So it's just what's the effect of February compared to January. It's the marginal effect. You could choose June, and then it'd be what's January compared to June. But it won't change the actual prediction.
I think whenever I did this Python stuff, this was a couple years ago, we could add seasonality to ETS models.
Mm-hmm.
Because it doesn't seem like that one was doing that, right?
It did. It just missed on the peak months. It was a little flat on the peaks.
Okay.
Or did I already pass that? Training data. So it still picks up the seasonality, right? It's high in spring and low in summer. So it gets that seasonality. It just missed a little bit on the peak months.
Okay.
Yeah, and so the Fable package uses some optimization criteria to find the best fit for the exponential smoothing part.
Do you have backtesting built in with these as well? Like it's kind of like k-fold cross validation.
Oh yeah.
But like with time series.
Yeah. So you can do cross validation. So here we have our pothole data frame. We're going to use the first 24 months as the starting point, and then add 6 months to each training set until we run out of data. And then you can use those training sets to fit all the models, and then get the test accuracy, average that accuracy across all the cross-validation chunks, and that's your cross-validated accuracy, which is a much more robust way of doing it, right? Because it might be that the 20% that I chose to hold out just happens to be hard to forecast or easy to forecast. Cross-validation will average out that variance. It can also be slower depending on how many things you need to do.
Yeah.
Right. And this is an example of the one step ahead of cross-validation. So it starts with 6 observations, whatever it is, adds 1 for each cross-validation chunk. And then you fit models on each training set, and then do accuracy, and then average that.
How do you like, are you able to add external shocks like I don't know, like the weird supply chain stuff that's right, like the dock workers.
Mm-hmm.
Have you managed to add that to your models, and like how would you?
You can, like for example, like I've in my blog I've actually done it. I've done the pothole forecast, but I've included weather data.
Okay.
How much rain, what's like the min, max, and standard deviation of the temperature in that month or something like that. And you can add those onto the ARIMA and linear models to get a little bit extra.
Okay.
But if you want to make a true forecast, then you need to know or assume what those values will be in the future. Right? I don't know what the minimum temperature is going to be next June.
Yeah.
Right? You could forecast that.
Yeah.
Right, but that's sort of an extra step.
Mm-hmm.
And then if your forecast for the temperature is wrong, then, or if it's close, then you're fine. But if it's very wrong, then your forecast that uses that exogenous variable is going to be off.
Okay.
Does that make sense?
Yeah.
if we have a little bit more time here, this is a graph of the autocorrelation of the pothole data. So there's really high correlations at lag 1, 2, and 3, and those are significant because it's outside of that dotted blue band. Anything within that is not significant. And then there's also correlation at 9, 10, 11, 12, and 13 approximately, right? So that's the autocorrelation, right? And it actually decreases in magnitude over time, which indicates that there's a trend as well. If it was only seasonal with no change with no slope, then there wouldn't be a change in magnitude of the autocorrelation. And then we have partial autocorrelation, which is the correlation between some observation and a lag of that observation that accounts for all the intermediary lags. And this is what you need to understand if you want to do things like more advanced models. And there's all sorts of great functions in this package that let you do this stuff. And this is one line of code, right? It's pretty straightforward. But this is more into the theory, like of understanding a time series, right? There's also time series features. So if you have a large set of time series features that you're measuring, and you need to understand them all somehow, there's a really quick and interesting way to do that. So this is the top 12 request types from that same data source. Potholes is among them, but we have 11 more, and you can see that they're all different, right? The first one is highly seasonal with almost no trend. There's some variance in seasonality, but no trend, right? We have some things that have really steep trends, almost exponential trends. We have things that are very, very intermittent, like snow and ice removal, like long streaks of 0, and then big spikes, right? Which is really hard to model, but that's a separate conversation. So, there's a variety of ways you can describe these. What's the average? What's the variance? What's the slope? If you fit a polynomial, what's the curvature? How many times does it cross the slope? How many streaks are there, like 0 or not 0? There's lots of ways to describe a time series, right? The FEASTS package, FEASTS, provides a lot of these. So this is, I threw everything the package had at those 12, and we get back, so I just chose the first request type, abandoned vehicle. We get 48 columns of ways to describe a time series, which is a lot. And they're all continuous, which is very helpful, in statistics. We have really easy stuff like how strong is the trend, how strong is the seasonality, spikiness, curvature, the autocorrelation stuff we'd already talked about. Oops. But there's also Shannon entropy, which is a really easy one-number way to describe a time series. I might have passed it already. Entropy, where's entropy? Spectral entropy, there it is. That's basically the noise to signal ratio. If it's 1, then there's no signal. It's all noise. If it's 0, it's all signal, no noise. So this one is mostly noise, be very hard to forecast. But that's a very easy one-number summary of a time series. And then we have 48 of these across 12 observations, right? So you can do some dimension reduction on this and then find some clusters or similarities on that, right? So this just does PCA on those 48 columns on those 12 request types. So the first principal component on the x-axis and the second on the y-axis. So potholes and weeds slash debris are very similar because they're both pretty seasonal. The snow and ice removal is on its own island because it's just so weird. You know, long streaks of 0 and then spikes, but no trend, no seasonality. So that's a pretty quick way to be able to ingest a large number of time series and just get a pretty good summary of them. Any other questions on the slides?
What is principal component analysis?
Yeah, it's a dimension reduction technique, pretty often used in machine learning. It's a way to condense a data set with a large number of continuous variables and extract the signal from those, and then reproject them onto uncorrelated components, right? So the principal component 1, 2, and 3. The first one will always explain the most variance in the data set, but it's a way to go from 48 to 2, but still be able to explain all the variance in that data set. Again, it's pretty common in machine learning, especially things like bioinformatics. If you have, 200 columns that describe the dimensions of some cell, you want to condense that because fitting a model with that might be very complicated and complex and costly. It might be better to condense all that information down into principal components. This is just one application of that. All right, well, that's the slides. I can do code walkthroughs if people are interested, but otherwise, thanks for coming.
Thank you. Do you have a link to the slides?
I've got it on my GitHub. I can put it in our Slack, on the Code Spy Slack if you're in there, and then this will probably end up on my blog at some point. I'll make sure that gets put out there.